Feedback on quiz 1. Feedback is information. The reason we do feedback is for improvement, growth, learning. That's why we're here. The first problem involved design of a rocket. Question A was, what does mass mean? Why care? Mass is the amount of matter a body has. Equally correct, we could have said mass is resistance to acceleration. Why care? The rocket motion is governed by F equals ma. And if mass is low for a given thrust force, we maximize acceleration. If we maximize acceleration, this maximizes the height, the speed of the rocket, all the stuff we care about as designers. The number one performance criteria is to reveal the physics. Explain the scientific and mathematical ideas and concepts. Why? It increases our odds of a valid solution. If we train ourselves to do it, it helps us learn the physics. And it also trains us to always start with valid concepts. Some tips. Use disciplinary language, things like acceleration, thrust. Notice I'm using vectors here. Number 2 tip is state concepts accurately. Any concept we use as engineers can be stated accurately in one short sentence, sometimes two. Tip 3 is be precise. Notice I subscripted force with external. This is the sum of external forces. I can improve this by subscripting acceleration with a g to indicate acceleration of the center of mass. Second performance criteria is to communicate with C5. And C5 is a shorthand with be clear, be concise, be complete, be convincing, be compelling. And why do we do this? It saves us time to be brief, and it's a much better means to explain to other people. How do we do this? Number 1, don't write a lot of words. Number 2, use math symbols. They carry meaning. They're kind of like music notes. Number 3 is abbreviate. You'll notice I abbreviated acceleration and thrust. Problem 1b asked, what does weight mean? And weight is the pull of a planet, for example, the Earth, on a body, for example, the rocket. And equally correct, we could have said weight is the pull of gravity on a body. It asks for 3 differences. First off, the meanings differ. Mass refers to the amount of matter. Weight is the pull on a body. Secondly, mass is the same everywhere. Weight varies with location. And third, the units are different. Common units for mass are listed here. Common units for weight are listed here. 1c asked, what does the derivative mean? The derivative is defined as a limit as delta x goes to 0 for a function at x plus delta x minus a function at x. And we can also write it like this. And I like to think of the derivative, and this is the most general meaning. It's a ratio of a change in a variable to a change in another variable in the limit as the variable in the denominator goes to 0. Why is it relevant? Well, many important variables such as velocity and acceleration are defined with derivatives. 3 ideas for improving. Tip number 1, get your concepts down. These concepts are given in the handouts, in the book, in the lecture, and the way to get them down is just practice using them in the real world. Tip 2, be concise when you write. No novels. We are engineers, not English majors. Tip number 3, avoid defining a concept with an equation. For example, if we said, what does a moment mean? And our answer was, a moment means the radius vector crossed with the force vector. That would be devoid of meaning. A moment means the tendency of a force to rotate a body around an axis. What an equation does is it relates 3 concepts. It relates the moment, which is one concept, the radius vector, which is another concept, and force, which is a third concept. The next problem on the quiz was actually problem 2.9 in the textbook. And the solution is worked out, and I've given you a reference earlier in the feedback so you can go through the solution. I want to talk just about the performance criteria. So the number 1 performance criteria, this again for the whole class, is reveal the physics. And you'll notice on my solution I laid out the total weight is the weight of the tank plus the weight of the oxygen We use Newton's law of universal gravitation. We use ideal gas law. The whole idea on revealing the physics is anyone should be able to look at your documentation and know exactly what equations and what concepts you use to solve the problem. You want to make this really super clear. Performance criteria number 2. Figure out the solution path with logic. And what that means is you always start with your problem goal and identify what do I need to do to reach this. And here there's 2 new goals. I wrote 2 equations for that. Again, I illustrate this with many examples during the course. The third performance criteria is apply units everywhere. Notice in my situation, I have units. You want to convert here to consistent units. Notice the goal has units. Notice down in the solution, grid method, and the answer has units. Everything about this has units on it. Next performance criteria. Define the problem so someone can look at your documentation and know exactly what the problem is. This might be true 1 year after the course is over. So you ought to be able to look at this and say, here's what's going on, here's what the goal is. Next performance criteria is get a valid answer. As engineers, we care about validity and about right answers. And of course, we're always working on great communication. Clear, concise, complete, convincing, and compelling. And hopefully as you look at my documentation, it's very easy to follow. But you always want to create documentation that communicates with other engineers. So tips for improving. First, the ideal gas law has 3 forms: the mass form, the mole form, and the density form. You always want to select the right form. Most students selected the mole form, and that would be a lot of extra work. The mass form is the easy way to do this problem. Here's probably the most important tip. Use consistent units. If you don't use consistent units, you go into unit conversion hell. And I saw that on probably half or 3/4 of the students' papers, just many extra unit conversions that were unnecessary. Convert your units to consistent units right at the beginning of the problem. It makes the problem so much easier. The third tip, there's a lot of performance criteria to work on. Just take one at a time. And what I recommend is that you focus on reveal the physics. That's the real key one. When you get that one down, start focusing on reveal the solution path using logic. And when you get that one down, start focusing on making a good situation diagram. So, in summary, I've described the performance criteria for doing great engineering. We define the problem we're trying to solve. We reveal the physics. We apply units throughout. We get valid answers. We communicate with C5. We structure our actions. And we figure out the solution path with logic. Again, our whole purpose, it doesn't matter where our present level of performance is really. That matters a little bit, but really our whole aim is to improve performance, to grow, to learn. And just remember, we're focusing on 2 ideas here. Let's keep this simple. We want to know useful things, and we want to be able to do useful things. That's why we're engineers.